Okay, Michelle, I'm really sorry. I forgot to record. I'm starting right now.
No, it was intentional.
It was not intentional.
No, he said, haha, Michelle's not gonna get a video.
We talked about babies.
We did talk about reproduction. It was very inappropriate. Okay,
Maybe it was a good thing
So-
I was recorded.
yeah, that's true.
We learned where babies
It was
came from.
incriminating.
It was incriminating. All right, so if A and B are in H, then A plus B is in H. All right, so Michelle, the notes will be posted though, and you really didn't miss a ton. You missed a little discussion of what closure means, but yeah, it was kind of inappropriate. So glad it wasn't recorded. No, A and, sorry, that's my shorthand for and. If A and B, it's supposed to be my ampersand. Sorry. Okay, last part then, let's suppose that A is in H. So we know what that means. That means that A can be written as this mess, x1 v1 plus x2 v2 all the way out to xp vp. Do we want to stay outside or do we want to go in? We're okay? All right. Oh, that's true. Okay, so what is the goal here? We're supposed to show closure under scalar multiplication. So what do we need to multiply A by? Any scalar, right? So if we take CA, well, CA is just going to be C times, can I just be lazy and put that like that? Just say C times all that stuff, which means that it's still going to be a linear combination of the vectors V1 to VP. It's going to be CX1 V1 and CX2 V2 all the way out to the end. So it's a little bit of a process showing that something is a subspace. Now, I'm going to have you guys try one a little bit later on from scratch, but it's easy to keep track of because it's just those three qualifications. If you can show those three qualifications, then you're done. Zoom people, do you have any questions?
So I'm a little confused. What's the difference between what we did for step 2 and step 3? Like I know step 3 was addition of two.
That's the only difference.
Vectors that were in it. Like once by finding the two vectors, didn't we prove 3 that the scalar multiplication is in? Because once we defined A as x1 times v1 plus x2 times v2, didn't it then prove also that scalar multiplication is also in A?
No, so go back to the definition up at the top where it says for each U and V and H. So how do we proceed? We pick the U and V and H. So we picked an A and a B, they're arbitrary, and that means that they can be written like this, as these two long expressions. Yeah, and then we said, now add them and see if that result is also in H. So when we add them, do we still get a vector that can be written as a linear combination of the others?
Okay.
And we do.
Why when you use C is many.
C at the bottom, C is a scalar. So C is some real number.
Can you use the difference?
Yeah.
C isn't like C1, C2, C3. It's just C, whereas the X's is X1, X2, X3, it's a vector.
Your table over there, are you guys okay? You guys? Fine? Carson? Yeah? Good? Okay. All right. So let's talk about non-examples of subspaces. And the easiest one to discuss is a line not through the origin. We're just going to stay in R2. So here's XY. And I want to prove to you that this thing violates all three conditions. I know, right? Okay, so think of this line as a set of points that lie on the line. It consists of infinitely many points. So clearly the origin is missing, right? Origin not on. So that shows we violated 1. 1 is no good. Okay.
Is there a way to say like not an element of?
Yeah. So the zero vector is not an element of this set H or whatever, or the set L since it's a line. Okay, now watch this. Let's take a vector that does lie on the line. So here's vector U. and here's vector v. Those two vectors lie on the line. Where does the sum of those two vectors lie? Yeah, you guys remember how to do it? What shape do we make? Parallelogram, good. So it's like this. It's going to be the diagonal of that parallelogram. So this vector right there, that's u plus v, which is not on the line. We'll say, yeah, not on the line. So that means item number 2 is violated. And then I think based on that reasoning, you can figure out why the third one fails as well, right? The third one fails because if u is, say, that vector, here's a cu. That's cu with a negative c, and that's clearly not on the line, right? Not on line. So a line through the origin violates all 3 parts of the definition. Of course, you only need to show that it violates 1, so you can really kind of stop after the first thing. You can say it doesn't contain the origin, so you're done.
What would that be considered a space?
Well, it's really not even a name. Like, it's just a line, you know? So if you think about, let's think about R3 for a second. Here are all the subspaces of R3. Ready? One of them is the 0 subspace. The origin is a subspace. It's a really trivially simple one, but it's a subspace. So we're going to list all of them. Next is all possible lines through the origin. That's another class of subspaces of R3, right? Okay, this is all possible subspaces of R3. All possible subspaces. Yep. Then 3 is all possible planes through the origin. And what's the last one? R3 itself. So this is where we get into this talk about dimension. This thing is a 0D subspace, then a 1D subspace, a 2D subspace, and a 3D subspace of R3. All the other stuff we could create, lines not through the origin, planes not through the origin, those things are not considered subspaces.
It kind of makes sense because whenever we're doing like many of the factors in our math, there's no way to know that something does not begin at the origin. The tail is always at the origin.
Yeah, in standard position, that's right. Yep. Okay, I think it's a good idea to pause for the video at this point, and I think that'll nicely introduce the rest of what we have to do. So the video is 12 minutes. Hope my computer's battery will last. Let's see, how will we do this though? Could you all just put in headphones and watch it on your own? Would that work? Yeah. Because I'm not gonna, if I play it to all of you, I don't know that, like, yeah, you can leave the meeting for now. You guys on Zoom, I'm gonna play it from my computer, okay? You can. Yeah, that's fine. That's fine. Let me unhook. No, I just want you to watch. I don't want you to writing anything down. Brian's AirPods are disconnected. Oh, they are? Not your AirPods. Can you all, if I just turn mine around, you're okay with that? My computer. Share.
George. That's such a funny way to spell it. You notice that?
I know. Both George. No, she's still not.
George.
I see her. She in our half-life of physics, she's teaching.
Welcome to Flatiron School. This is where you learn how the future works. Where the whole point of education is to get you a job in a
blue one round.
As you can probably tell by now, the bulk of this series is on understanding matrix and vector operations through that more visual lens of linear transformations. This video is no exception, describing the concepts of inverse matrices, column space, rank, and null space through that lens. A forewarning though, I'm not going to talk about the methods for actually computing these things, and some would argue that that's pretty important. There are a lot of very good resources for learning those methods outside this series, keywords Gaussian elimination and row echelon form. I think most of the value that I actually have to add here is on the intuition half. Plus, in practice, we usually get software to compute this stuff for us anyway. First, a few words on the usefulness of linear algebra. By now you already have a hint for how it's used in describing the manipulation of space, which is useful for things like computer graphics and robotics. But one of the main reasons that linear algebra is more broadly applicable and required for just about any technical discipline is that it lets us solve certain systems of equations. When I say system of equations, I mean you have a list of variables, things you don't know, and a list of equations relating them. In a lot of situations, those equations can get very complicated. But, if you're lucky, they might take on a certain special form. Within each equation, the only thing happening to each variable is that it's scaled by some constant, and the only thing happening to each of those scaled variables is that they're added to each other. So no exponents or fancy functions or multiplying two variables together, things like that. The typical way to organize this sort of special system of equations is to throw all the variables on the left and put any lingering constants on the right. It's also nice to vertically line up the common variables, and to do that you might need to throw in some zero coefficients whenever the variable doesn't show up in one of the equations. This is called a linear system of equations. You might notice that this looks a lot like matrix vector multiplication. In fact, you can package all of the equations together into a single vector equation where you have the matrix containing all of the constant coefficients and a vector containing all of the variables, and their matrix vector product equals some different constant vector. Let's name that constant matrix A, denote the vector holding the variables with a bold-faced X, and call the constant vector on the right-hand side V. This is more than just a notational trick to get our system of equations written on one line. It sheds light on a pretty cool geometric interpretation for the problem. The matrix A corresponds with some linear transformation, so solving AX equals V means we're looking for a vector x, which, after applying the transformation, lands on V. Think about what's happening here for a moment. You can hold in your head this really complicated idea of multiple variables all intermingling with each other just by thinking about squishing and morphing space and trying to figure out which vector lands on another. Cool, right? To start simple, let's say you have a system with two equations and two unknowns. This means the matrix A is a 2 by 2 matrix, and V and X are each two-dimensional vectors. Now, how we think about the solutions to this equation depends on whether the transformation associated with A squishes all of space into a lower dimension, like a line or a point, or if it leaves everything spanning the full two dimensions where it started. In the language of the last video, we subdivide into the cases where A has zero determinant and the case where A has non-zero determinant. Let's start with the most likely case, where the determinant is non-zero, meaning space does not get squished into a zero area region. In this case, there will always be one and only one vector that lands on V, and you can find it by playing the transformation in reverse. Following where V goes as we rewind the tape like this, you'll find the vector x such that A times x equals V. When you play the transformation in reverse, it actually corresponds to a separate linear transformation, commonly called the inverse of A, denoted A to the negative 1. For example, if A was a counterclockwise rotation by 90 degrees, then the inverse of A would be a clockwise rotation by 90 degrees. If A was a rightward shear that pushes j hat 1 unit to the right, the inverse of A would be a leftward shear that pushes j hat 1 unit to the left. In general, A inverse is the unique transformation with the property that if you first apply A, then follow it with the transformation A inverse, you end up back where you started. Applying one transformation after another is captured algebraically with matrix multiplication. So the core property of this transformation A inverse is that A inverse times A equals the matrix that corresponds to doing nothing. The transformation that does nothing is called the identity transformation. It leaves I hat and j hat each where they are, unmoved, so its columns are 1, 0 and 0, 1. Once you find this inverse, which in practice you'd do with a computer, you can solve your equation by multiplying this inverse matrix by V. And again, what this means geometrically is that you're playing the transformation in reverse and following V. This non-zero determinant case, which for a random choice of matrix is by far the most likely one, corresponds with the idea that if you have two unknowns and two equations, it's almost certainly the case that there's a single unique solution. This idea also makes sense in higher dimensions, when the number of equations equals the number of unknowns. Again, the system of equations can be translated to the geometric interpretation where you have some transformation A and some vector V, and you're looking for the vector x that lands on V. As long as the transformation A doesn't squish all of space into a lower dimension, meaning its determinant is non-zero, there will be an inverse transformation, A inverse, with the property that if you first do A, then you do A inverse, it's the same as doing nothing. And to solve your equation, you just have to multiply that reverse transformation matrix by the vector V. But when the determinant is zero, and the transformation associated with the system of equations squishes space into a smaller dimension, there is no inverse. You cannot unsquish a line to turn it into a plane. At least that's not something that a function can do. That would require transforming each individual vector into a whole line full of vectors. But functions can only take a single input to a single output. Similarly, for 3 equations and 3 unknowns, there will be no inverse if the corresponding transformation squishes 3D space onto the plane, or even if it squishes it onto a line or a point. Those all correspond to a determinant of 0, since any region is squished into something with 0 volume. It's still possible that a solution exists even when there is no inverse. It's just that when your transformation squishes space onto, say, a line, you have to be lucky enough that the vector v lives somewhere on that line. You might notice that some of these zero determinant cases feel a lot more restrictive than others. Given a 3x3 matrix, for example, it seems a lot harder for a solution to exist when it squishes space onto a line compared to when it squishes things onto a plane, even though both of those are zero determinant. We have some language that's a bit more specific than just saying zero determinant. When the output of a transformation is a line, meaning it's one-dimensional, we say the transformation has a rank of 1. If all the vectors land on some two-dimensional plane, we say the transformation has a rank of 2. So the word rank means the number of dimensions in the output of a transformation. For instance, in the case of 2x2 matrices, rank 2 is the best that it can be. It means the basis vectors continue to span the full 2 dimensions of space and the determinant is non-zero. But for 3x3 matrices, rank 2 means that we've collapsed, but not as much as they would have collapsed for a rank 1 situation. If a 3D transformation has a non-zero determinant and its output fills all of 3D space, it has a rank of 3. This set of all possible outputs for your matrix, whether it's a line, a plane, 3D space, whatever, is called the column space of your matrix. You can probably guess where that name comes from. The columns of your matrix tell you where the basis vectors land. And the span of those transformed basis vectors gives you all possible outputs. In other words, the column space is the span of the columns of your matrix. So a more precise definition of rank would be that it's the number of dimensions in the column space. When this rank is as high as it can be, meaning it equals the number of columns, we call the matrix full rank. Notice, the 0 vector will always be included in the column space, since linear transformations must keep the origin fixed in place. For a full rank transformation, the only vector that lands at the origin is the 0 vector itself. But for matrices that aren't full rank, which squish to a smaller dimension, you can have a whole bunch of vectors land on 0. If a 2D transformation squishes space onto a line, for example, there is a separate line in a different direction full of vectors that get squished onto the origin. If a 3D transformation squishes space onto a plane, there's also a full line of vectors that land on the origin. If a 3D transformation squishes all of space onto a line, then there's a whole plane full of vectors that land on the origin. This set of vectors that lands on the origin is called the null space, or the kernel of your matrix. It's the space of all vectors that become null, in the sense that they land on the zero vector. In terms of the linear system of equations, when V happens to be the zero vector, the null space gives you all of the possible solutions to the equation. So that's a very high-level overview of how to think about linear systems of equations geometrically. Each system has some kind of linear transformation associated with it, and when that transformation has an inverse, you can use that inverse to solve your system. Otherwise, the idea of column space lets us understand when a solution even exists, and the idea of a null space helps us to understand what the set of all possible solutions can look like. Again, there's a lot that I haven't covered here, most notably how to compute these things. I also had to limit my scope to examples where the number of equations equals the number of unknowns. But the goal here is not to try to teach everything, it's that you come away with a strong intuition for inverse matrices, column space, and null space, and that those intuitions make any future learning that you do more fruitful. Next video, by popular request, will be a brief footnote about non-square matrices. Then after that, I'm going to give you my take on dot products, and something pretty cool that happens when you view them under the light of linear transformations. See you then.
Cool. Wonder what I'll feel like seeing. Okay. That kind of makes matter. During first semester when we were learning about vector fields and like stuff with gravity and physics, and also in this class, I looked at space black holes. There's this thing called spaghettification. Yes.
Okay, Zoom people, can you hear me?
Yes.
Can someone say yes if they can hear me?
Pull you apart. And they're like literally a string of singular atoms.
Yes.
Yes, thank you. Okay, great. All right, let's take those ideas in the video and yo, WTF is this? Yeah.
Who said that? Daddy can't see them.
Okay, so I'm letting everybody in who wants to see. There, I think that's everyone. Is that everybody, or do I need to keep waiting for people to join? Good? There's Caleb. Okay. Okay, so let's define column space. Would one of you define it in your own words? What would you say?
Column space
Space with the columns occupy.
Eh,
the dimension is
what? Of what vectors? Yeah, it's the span of, it's the outputs, it's the range, it's the span of the columns of the matrix. So the column space of a matrix A is the set, and it's usually abbreviated call A like that, C-O-L-A. So the column space of a matrix A is the set call A of all linear combinations of the columns of A. It's a set call A. This is just the way that it's written. It's the notation. It's the set call A. All right. Is it a subspace?
Not the yes.
think about it.
What's another way of saying the set of all linear combinations? Span. Didn't we already prove that span's a subspace? Yeah. So this is also a subspace, okay? So if A is made of, usually we're talking about it, then call A is just the span of the columns of A. So it's span A1 all the way out to AN.
Mr. Cope lied at the beginning of the semester. He said that my ability to draw nice brackets would be getting better, but it has
And
not.
it hasn't. I'm sorry. We haven't practiced it enough. So sorry. Yeah, it's not very impressive. You're right. Okay. So this means that your column space might have full rank, right? So what you learned in the video about full rank. Rank could be 0 to n, anything 0 to n. If your rank is 0, that means that your columns only span the 0 vector. If your rank is n, that means your columns span all of Rn. But they could span some lower dimensional subspace of Rn, right? So you could have, what this means is it's kind of like, how many essential vectors do you have? You might have a whole bunch of vectors, but if they span only a plane, you really only need 2 essential vectors.
Wait, so when you say 0 minus n,
No, sorry, 0 through n. Sorry,
Oh.
I should have said that differently. I'm sorry. This line is through 0 through n. So it could be rank of 0, could be rank of 1, all the way down to rank of n, which you learned is called full rank, which is where that's where the, put it in different language, you guys. Put it in transformation language. When something is full rank, what does that mean?
Yeah.
Yes, good. What else?
Pivot in every. No, it's square.
Square, good. You could have said what you were going to say. Pivot in every row and column. What did you say? Good job. It's onto and it's 1-to-1, right? And remember that funky vocab word we learned called codomain?
yeah, the codomain is the same as the range.
When the rank is full, the codomain is the same as the range. That's right. Okay, so over and over in different terms. That's what we're seeing here.
When the rank is full, the codomain.
Yeah. So this
Maybe
is
eventually
full
I'll
rank.
go on to 1-to-1.
It's same as
Full rank is the same as when the range equals the codomain. That's important. I should help you with that. No, seriously. I want to make sure you can do that by hand.
I can nearly do it.
Matrix multiplication of 2 by a 2 by 2. Example. Is B in call A? Is B a member?
Thing is moving. Oh, there he is.
Okay, good. That's a -4. Sorry about the swap. -4.
Better.
I will try. Okay, I copied it down right. Okay. Okay, put this in transformation language for me. How else could we say it?
So does A times X equal B?
Say more about that though.
Well, we're trying to find an X that satisfies that equation.
Good job. So this is really asking, does AX equal B have a solution? Or put it in terms of like visuals that Grant Sanderson would use.
Be within the span of.
He would use more visual language though, I think.
You would say, can you reach B by it having some linear combination of A, or you moving around?
Yeah.
You go,
So can we move vectors so that B is where we land, right? Can we move vectors so that B is where we land? So how do we answer this?
You ref.
You always ref in this class. That's exactly right. So let's try and figure it out, okay? So here we go.
is there a way to like write notation like A augmented with B? You know what I mean?
Yes. You do a little, just put in A and then dash lines and then B. I'll show it in the notes in 1 second. All right, so I'm about to ref. and it's going to be a 3 by 4. And the first row is 1, -3, -4, 3. 1. I feel like I'm smelling campfire.
It does smell good. I love
Are you
it.
smelling that?
Are you a fan of campfire?
I am.
I do like campfire. I feel like
They've never been.
no, I mean not even just being camp, like being outside.
Yeah,
Like when I smell like it, I like it, but when other people come in
it
smelling
sounds like a great idea, except that grill is missing a handle. So unless anyone wants to do this while it's hot, I don't think so.
That's actually like
You know, I want some. That they might have intentionally done this though, don't you think? So that people didn't.
I wonder how often it got used that they decided they were gonna buy one. You know what
Yeah.
I mean? Like they weren't just gonna like outfit the
I have to tell you, one time when I taught summer school, the kids decided that on one of our breaks they were going to bring like steaks and chicken to grill during our break. And I don't remember if they used this or if they used like one they brought, you know, like a George Foreman or something. It was so funny.
that is
They got away with a lot of stuff in summer school because I was like, oh yeah, sure, why not? It was like geometry or something, mostly retaking, you know.
Oh.
good for them, honestly. Makes most of it.
Exactly.
Kind of feels like summer story.
Okay, so let's put this on our page and let's talk about it.
I've done this twice. It's how welcome for expression here. Because
What did you want to say? Okay. Oh, it did work nicely. Oh, you're right. Okay, that's the matrix. Whether you write it down or not, I don't care. If you want to, you can. I just bereft it. Okay. So this means that not only do we have a solution, the answer is definitely a yes, we have multiple,
oh, yeah, so like right there. I forgot what that was.
right? We have a free variable.
One there. No problem. Okay.
Okay. What's the rank? Is this full rank?
No. It'd be going like from
Not
all of our
full
three
rank.
planes.
I
That's
thought it was
right.
the amount of columns there.
But it's the amount of columns that are pivot columns.
Oh.
Yeah.
Okay.
So we only have 2 pivots. So the rank here, we'll talk about rank more formally later. The rank here is equal to 2 because the column space is only a 2-dimensional subspace of R3. The column space is only going to be a plane. Okay. Now, could we find the values for X? Yeah, we could. We don't care about that though. We just say that yes, there is a solution. Therefore, B is a member of col A. We already did kind of. Does AX equal B have a solution? Yes. We can say B is a member of col A. So because AX equals B has a solution, there are scalars that we could find to put on the columns of A to reach B. Want me to show you one? Here, look. X1 equals -9/2 minus 5x3. X2 equals -5/2 minus 3x3, and X3 equals X3. So let's pick a value for X3. Let's pick 10 for X3.
They had to be introduced artificially.
-9/2 minus 5 times 10. There's the first variable we're going to use. Then -5/2 minus 3 times 10. There's the second value we're going to use. And then we're going to use 10 for X3. Okay, so here's what this means. If I take the original matrix, I'm going to get rid of the ref. And I'm also going to get rid of this last column. So we're only working with A, okay? Okay, you agree that's A? And now I'm going to multiply it by a vector. -109/2, -65/2, and 10. The output better be B. Let's see if it is. 3, 3, -4. It worked. So that vector that I put there, the -1/9/2, the -65/2, etc., that's one of the infinitely many vectors that becomes 3, 3, -4 after the transformation. Follow that okay?
Sure.
Want to ask more?
No, I don't have a question. Don't really get what's going on.
Okay. So what we're trying to find is does B lie in the range? Is B a possible output to this transformation? And we just proved that it is because we found an input that produces that output. And we did that by refing. We did that by essentially solving the system. Okay?
So are we trying to say, like, is B in the subspace col A? and it's wait.
We're trying to say, is B in the
Is
subspace
B in
call
the
A?
subspace of call A, and the subspace call A is all of these.
Not only all of those, but all the combinations of those as well.
Plus all of their combinations.
Yeah, that's right.
Okay, yeah, so it's the span of, okay, so it's just the span of A.
Uh-huh.
Okay. This is,
Careful, it's not the span of A, it's the span of the columns of A.
yeah.
Would all matrices be subspaces?
All matrices have a column space. And all matrices have a column space. It's a subspace because we proved that the span of a set of vectors is a subspace.
That's what I was like trying to figure out, because you can't have like a matrix that represents a line. That's
Yeah.
not possible. Like a line
Right.
that's not.
Right.
That's not possible.
Right. Okay, all right. Column space, good. Questions on column space? Zoom people, questions on column space? Okay, this is by far the most productive class I've ever had outside.
Yeah.
Well done, everyone. Well done. I know. No, it's a compliment toward you. It's good. I'm glad. Okay, all right, now, the harder one from the video space. Let's define that, okay? So the null space, it's another subspace, and that's going to be your job. You guys are going to prove to me that a null space is a subspace in just a minute. Okay, so the null space of a matrix A is the set, it's usually abbreviated null A, like this, N-U-L-A. I know, right? That one extra letter was too much. Okay, so the null space of a matrix A is the set null A of all solutions of the homogeneous equation AX equals 0. Hello.
Hi, theory.
You know those people? No. AP Music Theory, yay.
Christian took BC last
Let's,
year.
let's do some ear training. Oh. Oh no. Oh no. Well, you're getting AP credit, so that's good.
Yeah, we're not.
Yeah, that's true. You get easier AP credit. You don't have to take an AP test.
But none of our schools are going to allow us to use.
Illinois does, yeah. Yeah. Oh, several of the Big Ten schools do, yeah. Okay. What the heck does this mean? Can you put this in language that an Algebra 1 student could understand? What do you think? What do you think? Are you thinking? Put this in language that an Algebra 1 student could understand.
So it just moves that to jump through. But
That's right. But that's not a way that an Algebra 1 student could understand. Well said, though. It's all the things that become the zero vector.
Yeah, I'm excited.
Okay, fine, but I think they can understand more than that. What about your table? You got any ideas? Okay, watch this. Everybody watch this from Algebra 1. Everybody write down this function, please. F of x equals x plus 3, x minus 5. Yes. Okay, so Cody just got it. When I wrote down that function, that triggered in his head what you do with that. You would usually find the zeros of it, right? So the null space is literally just the zeros of the transformation, okay? So if I were to ask you for the zeros of this, you guys would tell me it's -3 and 5, right? Because those two numbers are the two values that produce 0 as an output, right? F of -3 is 0 and F of 5 is 0. So the null space is literally just the stuff which becomes 0 under the transformation. So the null space can be thought of as the zeros of the transformation which takes x and maps to ax. Or, you know, we used to write that as t of x equals ax.
You forgot the other
Huh?
quotation.
Oh, yeah, I did. The zeros of that transformation. Okay.
So wouldn't that be the zero vector?
Well, okay, great question. So the zero vector is always a member of null A because the zero vector always maps to the zero vector, right? The question is there more than that? If it's that's right. So if there's only a trivial solution, then it's just the zero vector. But if it's more than just a trivial solution, then you've got a linearly dependent set, you know? Got it? Okay, now you guys are going to do this for me as formally as you can. I want you to prove that the null space is a subspace. Okay?
We just said linearly.
And, well, it only would be for some cases. So here's the task. It's 307. I want you to prove that the solutions to AX equals 0 is a subspace. And I'm just gonna over here.
Is the trivial solution, right? What if it's, so yeah, the first one is that you have to zero vector.
So yeah, the first question is 0 a member of this set? And it is because why? No, because a times 0 equals the 0 vector.
A is in the vector that leads to 0.
Yeah.
And then B also leads to 0.
Yeah, if you add them together, they just make another vector on that space that goes to 0.
Okay, I want that proved like with symbols. Because the intuition is good, but we have to show it. Am I muted? No, I'm not. I'm not muted. Okay, you guys who are at home, think about the three sets, right? Think about the fact that you want to prove that 0 is a member. You want to prove that if two things that we already know are members are added, they're still a member. And then we also want to prove that if you have a member of this set and you multiply by a scalar, you're still going to get a member in the set. Think about that for a few minutes.
Okay, I'm not following. I'm thinking, I don't know how to prove it. Like, I can think of examples where it would work. Well, the thing that I'm struggling with, shouldn't there only be the trivial solution?
Unless they're literally dependent.
But why would it be, why would that, didn't we just say that a subspace has to be linearly dependent?
No. Put every scalar at 0, it equals 0. That's all we said. So now we're saying there's some other combination. Let's say that we had like 1, 1, 1, 2, 2, 2, 3, 3, 3. So 1, negative 2, 0 would be a solution. So that's a non-trivial solution. You see how there's infinitely many.
So yeah, I think we were thinking about full rank.
Yeah. Full rank.
Because we could do
And only, yeah.
I see.
so there's and that could go on.
I don't know how to word that. Because if the trivial solution is going to, okay, well, I think I get it. If you have a trivial solution, I get that, right? The solution is if the subspace is a line. 0 plus 0 is still.
Anything written down yet? No? Part one is important though.
Yeah. That makes sense because U and D have to be.
So
because U and D are if you have like 0 plus 0, if you add.
What? Go ahead.
Well, so we're trying to
and sort of see how I would do it.
Oh, right. Yeah, we're working with the same code.
I know.
Okay, so for closure under scalar multiplication, I mean, anything times 0, 0, so you would just do C times, or so if we already had AU equals 0, C times AU
Good job.
is going to be 0.
I overheard that. Very nice. Okay, it's written now. Look, if U and V are in null A, is U plus V also in null A? That's the question. And so, hey, if U being in null A is a given, then that means that AU equals 0. If V being in null A is a given, that means that AV equals 0. So the question is, what happens if we take A times U plus V? The question is it going to be 0 or is it going to be something else? Well, A times U plus V is, we learned this a long time ago as a theorem, right? It's AU plus AV. But we know that AU is 0, and we know that AV is 0. And 0 plus 0 is the 0 vector. So we've proved it. This means that U plus V is also in null A. Okay, shoot, we've got item 1 done. We've got item 2 done. I'm going to write up item 3 really quick, and then we'll be done, okay? So if U is in null A, what does that mean? AU equals 0, right? We've got to show that CU is also in null A, meaning that A times CU equals 0. So let's investigate. A times CU. An old theorem tells us that I can take the constant out and write that as C times AU. But what is AU? 0. So this is C times 0. And what's C times 0? Yay, which means that this thing right here, this is a solution to AX equals 0, which means it's a member of null A. Okay, so here's what we know so far. We know that any span of vectors is a subspace, and we know that the solution to a homogeneous system is a subspace. That's a big deal, because that's basically everything we've encountered so far, except stuff that's AX equals B. Okay? Basically, yeah. Okay, I will post an appropriate amount of homework online. Y'all are free to go. Thanks so much. Have a great evening.